Hello, I am Javier Diez González from the University of León, from the Department of Mechanical, Computer and Spatial Sciences, and I'm going to present the paper entitled Stable Performance Under Sensor Failure of Local Positioning Systems. The index that I'm going to follow in my presentation is the introduction, local positioning systems overview in general, particularizing in the TDOA architecture, our previous works and the research proposal for this conference, the fitness function of the genetic algorithm optimization that we are going to present in this paper, a general overview of the scenario of simulations and the parameter configuration, and finally the results of the paper. As introduction, global navigation satellite systems have provided global coverage with reduced costs, but however, they are not able to reach the required accuracy for some particular tasks. This has promoted the emergence of some promising technologies for achieving valid results for these precision activities, which are known as local positioning systems. The main objective of the LPS is the design of an ad hoc sensor network for meeting the design requirements in accuracy for this kind of activities, such as precision farming, indoor and outdoor navigation of autonomous vehicles, or AGVs, automatic ground vehicles, that are very popular in the manufacturing industry in the last few years. As overview of the local positioning systems, we had to develop and to clarify that they are classified depending on the physical property measured for performing and for achieving the target location. They are based in time-based, frequency, angle, phase, power, or combinations of them, for which the time-based positioning localization has been the most used in the last few years due to their trade-off among robustness, accuracy, availability, and system costs. Among them, the TDOA systems, which are used in GNSS applications, and TDOA and ATDOA systems, which particularly fits the requirements of LPS, have stand out. Through the TDOA architecture is based in the emission of a positional signal by the target, which is received in two different coordinator sensors. We perform and collect the time measurement through the determinations of the different differences in time from the resection of the positioning signal in two different receivers. This promotes some hyperbolas in 2D spaces and hyperboloids in 3D, which must be solved for determining finally the target location. At least 4 different hyperbolas and 4 different hyperboloids are needed to finally calculate the position of the target without ambiguities, but we have shown in our previous works that under optimized node locations, we can get unequivocally the target location only by 4 hyperboloids in 3D positioning systems, which requires 4 different receivers. We have also used and have demonstrated and promoted a genetic algorithm optimization for finding this optimized node location, which is particularly important in LPS applications, since the reduction of the uncertainties can only be achieved through the optimized node location. For this task, we have proposed a methodology for finding this optimized node location, which is based in two different regions. One of them is the NLE, the node location environment, which is in blue in the figure in the left, and also the possible locations in which the nodes can be located, which is known as the NLE, the node location environment. The positions in which the target can be located is the target location environment. For reducing the uncertainties, we have used the Kramer-Rao lower bound, which is a maximum likelihood estimator, which provides the minimum uncertainty in the position determination of a target, considering noise and clock errors. In this context, we have shown that under optimized node locations, we are able to reduce the system uncertainties, and we have also the possibility to reduce one of the receivers required for finally determine the target location. In this sense, we propose in this paper that we can achieve a configuration of the nodes in which we can reduce the necessity of having only 4 sensors under coverage for calculating the target location, but also we had to enhance this kind of distributions in cases of failure of one of the architecture sensors. In this sense, we propose an optimization with 5 sensors in which any one of them can be malfunctioning, and the optimization is not only looking for that nominal condition of 5 sensors. We are optimizing also for the cases in which only 4 of them are being used. In this case, we propose a fitness function which is covering the cases in which only 4 sensors are used. We must enhance the system operation by reducing the ambiguity in the position calculations with 4 nodes, which is the second term, and the last term, which is promoting the nominal performance of the optimization with 5 sensors. For this, we propose a scenario of simulations in which there is the node location environment and the target location environment regions, and the parameter configurations for the simulations. The results have finally enhance the proposed methodology, since the configuration 2 is not considering failure cases in which the malfunction of one of the sensors is not happening, and in failure conditions, the root mean square error of the architecture is quite higher than in the first configuration in which we are considering failure cases. We also boost the performance of the convergence radius, which permits the position disambiguation in cases of 4 sensors functioning, which is really noted in the first of the configurations with regards to the second one. In this case, we can see the good performance of the methodology by considering sensor failures in the red one of the sensors promoted in this optimization, in which we can see all the target location environments with a very good performance in convergence and also in accuracy. These are the references that we have used in this presentation, and many thanks to all of you for being there, and enjoy the rest of the conference.